We covered general notion of spatial decorrelation, and then we moved into spatial process modeling. And we saw that it's really all about modeling a covariance, which is a spatial covariance when we can give it a spatial interpretation. And we saw a fundamental difference between simultaneous process modeling, which is a model for the pattern as a whole, and conditional process modeling, which is really more appropriate for spatial prediction, given some observations, what are the values at unknown observations, or which are really suitable for Bayesian hierarchical modeling, where they then become a prior for the parameter distribution. And we'll talk a little more about that on Wednesday. So what I'm going to do this week is kind of give you an overview, a brief overview of the basic specifications. How do you bring spatial effects into a regression model? And you see that, I mean, once you get the main concept, it's actually pretty straightforward. But then, as always, there's different ways of doing it. What we'll focus on today is spatial dependence, and then Wednesday we'll focus on spatial heterogeneity, and that's where the hierarchical Bayesian thing will come back in when we talk about random coefficients in models. So I'll start by saying something about spatially lagged variables, which is the most straightforward way to bring spatial effects into a regression specification on irregular data. So on grids or lattice data, as they're sometimes called, it's a little easier because you know exactly where it's north, south, east, and west. On irregular data, it's much more complicated. And then we'll see the two main models, the spatial lag model, which has a spatially lagged dependent variable, and then the spatial error model, where the spatial effect is relegated to the error term. And we'll see the difference between these two, what that means for the model in terms of misspecification, meaning if you don't take the spatial effects into account, what does that do to your other parameters? And then I'll spend a little bit of time on two models that have received quite a bit of attention in the recent literature, and from my perspective, or according to me, often not exactly with the full awareness of what the implications are. So I'll spend a little bit of time on that. In terms of the readings, most of this is covered in detail in the text and also in the review chapter. The little article on spatial externalities shows you a range of specifications and basically emphasizes the difference between global spillovers and local spillovers. And the tendency in the literature today, at least in economics, tends to be to favor local models. But whether or not that is appropriate is really, at the end of the day, an empirical question. So that's not something you can decide a priori. But then, in terms of additional papers, I give you the reflection problem, which is a classic paper by Mansky, which especially if you have more of an economic interest, you should at least take a look at. And then two recent papers that kind of, should I say, criticize the traditional way of doing spatial econometrics. One pushes this local model, the SLX model, which is spatially lagged explanatory variables, which is kind of, in a way, a simpler model because it doesn't require any special estimation techniques. And then the other is a critique, as you can tell from the title, mostly pointless spatial econometrics. Basically, it's a classic standard economic critique of causality in these models. So basically, the bottom line is that you cannot always interpret these models in a fully causal sense, but from my perspective, that doesn't mean that they're not useful. Economists then call them descriptive models, but that doesn't mean that they don't give you useful insights. So let's start with this concept. Yeah.
So this last paper is about just all regressive models, or it's about?
Yes, primarily. So the critique by Givens and Overman is basically saying that the how should I say, the kind of standard practice of doing a specification search and going to a lag model or an error model ignores the fact that there's a lot of endogeneity and that the causal interpretations of these models may be very difficult. That's basically the point. But, you know, if you read it carefully, it doesn't say that these models are not appropriate. It does say, you know, it depends what you're trying to do, right? And if you have a full, you know, a properly specified model, I would argue that you can make a causal interpretation, especially if you have panel data. Cross-section is always going to be a little tricky, no matter what, you know, because you have to kind of, the causality has to come from your conceptual model. It doesn't come from the data. But if you have time and space, then the time dimension helps you a lot in terms of at least some notions of causality. I mean, this whole book's written on what causality means, so, you know, it's not a simple concept. So it's probably never going to satisfy everybody, but at least to some extent you can draw meaningful conclusions, and that's all I really care about. Okay, so how do we specify spatial dependence? And here again, as I've pointed out a number of times already, there is a major difference between the time domain and the cross-sectional domain. And so in a time domain, it's unambiguous what an observation shifted in time is. You know, everybody knows what one previous time period is. In space, that's not that straightforward. On a regular grid, regular lattice, you can go east, west, north, south, and so in a lot of remote sensing, for example, you have a grid structure, so there isn't any ambiguity, but that does not translate well or extend well into irregular layouts. You know, if you have counties, some have 4 neighbors, some have 5 neighbors, you know, you can't have a strict analog of the shift in space for irregular layouts. So then I introduced this notion of a spatially lagged variable, which is almost similar to a distributed lag in time series, which you don't see very much anymore, but it's a weighted average. It's a weighted average of the neighboring observations. So if we have a vector of observations, y, with the observations at the different points in space, then we just use the spatial weights to make an average. And since the spatial weights typically are row standardized, this is a straightforward average. And as I pointed out a number of times already, these weights tend to be very sparse. So there are lots of zeros in there. You know, there's only 4 or 5, 6 that are non-zero, so this is really easy to do. And so then these spatial lags, you know, can also be written in matrix notation. We're used to this by now. So we have spatial weights matrix W and Y. We saw that last week when we looked at the autoregressive models. That was a spatially lagged variable as well. So then what does this do? Because it is an averaging, it smooths the variability. So it has a smaller variance. It's similar to a notion of a window average, but it's important to think about this. This will come back when I talk about the reflection problem. Is that unlike in a lot of these spatial social interaction models in economics, where there is an endogenous effect or an effect, we'll see the different types in a few minutes, the effect of the context. And the context is modeled as the average. So, for example, rather than having individual incomes for each person, you would take the average income for all the people, average for a census tract or something like that, right? But that average includes the observation that you're looking at, right? The difference with a spatial weight is that, as we know, the diagonal is 0. There's no self-neighbor. So this, even if you have a spatial weights matrix that is all ones, no, row standardized, except for the diagonal, each term will be different because each term does not include the value at that location itself, which is a big difference with, in a lot of other analyses, you have moving windows, and the moving window basically takes an average of everything in the window. This is also sort of a moving window, except that the value at the location itself is not included. So it's different in that respect. So then we have a number of different kinds of models. We have, when we include a spatial lag of the dependent variable, we have what I call a spatial lag model, or strictly speaking is a spatial autoregressive lag model. If we have the spatial lags of the explanatory variables, the x's, so wx, that's used to be called a spatial cross-regressive model. In the more recent literature, it's called an SLX model for spatially lagged x variable model, but it's the same thing. And a lot of this recent literature doesn't necessarily know that this was done 20 years ago, but because it doesn't require special estimation methods, it really hasn't received a lot of attention in the methodological literature for spatial econometrics, but because there's nothing to do, you just use your standard methods, right? As opposed to the spatial lag model and also the spatial error model, where you do need to use specialized estimation methods. So that's where all the focus has been. So it's very straightforward. We have a problem. There's no easy way to incorporate this notion of a shift in space. So we move to the next best thing, which is an averaging of the neighboring values. We bring these averages in to the model, either for the dependent variable, wy, for the explanatory variables, wx, or for the error terms. First, I want to spend some time discussing the spatial lag model, because it is the most substantive model of the two being the lag model and the error model. So it's very frustrating, because the spatial lag model is actually a formal model for spatial interaction. And so I call that substantive spatial dependence. The problem is, however, that we don't actually have interaction data. Now, some of you with your flow data, in some sense, that is interaction data, but only one way. You don't have the other way coming back. At least some of you with taxi data do, but some other data you don't. So, so you're trying to model these interactions, which is an n-square phenomenon, through n observations, cross-sectional observations. So that's, as we discussed earlier, that's why we need the spatial weights to get us around that problem. And so then we're going to simplify the problem. Rather than modeling something in an n-square dimension, we're going to go with the cross-section, and we have a parameter, our spatial autoregressive parameter, and a weights matrix. And the interaction is then obtained by combining the two. And that's why I keep stressing, the parameter by itself as such doesn't really mean that much. You have to look at it together with the weights. If the weights are large numbers, your parameter will be small. If the weights are small numbers, your parameter will be larger. The product of the two will be the same, or can be the same, right? It's the product that you're modeling. To some extent, this is an identification problem, right? Because you have a product. If you switch the two around, then you can't tell one from the other. So it's not quite that extreme, but it's a little bit like that. So you can only interpret the autoregressive parameters if you know what's in your weights matrix, right? So of course, that's a problem, because we're trying to model something literally in 2 dimensions by only looking at it from 1-dimensional perspective. So that's imperfect. And there's a lot of criticism of the use of a weights matrix, an exogenous weights matrix, but the solutions basically are no better, right? So whether you take a weights matrix or you replace that by a distance function with a parameter, at the end of the day, there is no way you can model all the interactions. You have to simplify the phenomena, structure the phenomenon. So whether you structure this by a weights matrix with a coefficient or by a distance function with a coefficient is basically a matter of taste in the end, right? So there is a little bit of literature on a theoretical motivation for a spatial lag model, which is the equilibrium outcome of a spatial interaction process. So you can think about this almost like a game that operates over time, and then if it operates long enough so that it has reached an equilibrium, then the layout that you see across the observations of the outcomes, whether these are incomes, house prices, employment rates, crime rates, will follow or can be modeled by a spatial autoregressive process. So that is the behavioral motivation, and formally this is often referred to as a spatial reaction function, and I'll spend a few minutes on that. There's also a much more down-to-earth and practical motivation, and that's a data problem, a scale issue. And I may have mentioned this example before where I was modeling hedonic house price functions for individual house transactions in the Los Angeles area, and I had huge coefficients for a spatially lagged term, very high, 0.8, something like that, which basically means that everything is the same. And so there isn't really a good behavioral explanation for that, but if you think about it, it has to do with scale. And these developments in the Southwest are built by large developers, and they plop down 2,000 houses that are almost exactly the same. So if you're doing hedonic modeling and you model the price of the house as a function of its characteristics, there's not going to be a lot of variability there. And everything in statistics is about variance, variability, right? So if there isn't enough variance, then you have a problem in that you don't have as much information as you would have in an independent, uncorrelated world. And so you can look at the spatial lag model as a way to correct for that, as a way, if you wish, to keep you honest, to properly reflect the larger degree of uncertainty you have about the model coefficients and the other parts of the model. So that's kind of a non-behavioral practical thing. So if you have an advisor who doesn't like the interpretation of a spatial lag model that you happen to find through a specification search, then your plan B is to say it's due to the scale of the data. In other words, you're analyzing the data at too fine-grained a level, and there is insufficient variability at that level. So what do? You scale up. You can aggregate. This is one form of the modifiable areal unit problem. And if you scale up and group or cluster the observations that are very similar, then between the clusters, again, you can have the variability which you need for statistical explanation. Okay, the spatial reaction function, just a few minutes, a little bit of elaboration. So basically, it is a formal function where you have a decision variable that is expressed as a function of other decision variables. So, your labor supply is a function of the labor supply of others in the market, just to put it that way. And so what enters into this reaction function is both the actions of the other agents as well as resources that are available. Labor, capital, environmental resources. So if this reaction function is linear, then you can show that its form takes on the form of a spatial lag model. So that would be, if you wish, the most theoretical foundation for such a specification. And there's two ways you can get to it. There's this interesting article by Bruckner which shows that you can think of it directly as a spillover effect where the actions of other agents enter directly into the utility function of a given agent, and then if you solve that out, you can end up with a reaction function. That's called the spillover model. Another way is where you don't have the actions themselves, but if you wish, the consequences of the actions that enter into the utility function. So the resources, the drain on the resources, right? So your water is polluted, so you deal with polluted water, but the water is polluted because your neighbors polluted it. So the actions of your neighbors affected the resources. If that is the case, then if you, again, work out the math, it's very simple algebra, you end up with one of these linear reaction functions again. So that's the behavioral motivation. There are some problems with this model, and from my perspective, the most important one, and I've already mentioned this a couple of times, is what we call the inverse problem. And the inverse problem is that we see patterns, but we model processes, right? So we have a given pattern, you can call it a map of the data. How did that map get there? You know, is it a spatial autoregressive process? Is it a spatial moving average process? Is it some other process? Is it heterogeneity rather than dependence? You know, there's a classic identification problem which deals with true or spurious contagion. So for example, if you look at you know, disease data and you find that everybody in a village has a particular disease, that's the pattern, right? The inverse problem is, how do they get this disease? Do they get this disease because, say, their water is contaminated? So that would be a case of spatial heterogeneity. Contaminated water means they get sick, right? Or did they get the disease because of a contagious process where somebody came in with the disease and spread the disease? You can't tell. With cross-sectional data, you have a real problem. So this is something to keep in mind. Again, having data for space and time helps you out of this to some extent. Then there's the two more fundamental critiques. Fundamental is the wrong word. More theory-based critiques. One is called the reflection problem, which is in this famous paper by Mansky, and it has to do about which parameters can be identified in a spatial social interaction model, or more precisely, under what conditions can the parameters be identified in such models. And then, as I mentioned before, the new economic geography critique, which really has to do with causal effects. It doesn't really have to do with spatial per se, it has to do much more with it's a critique of the, if you wish, ad hoc and mechanical nature of, at least perceived by those authors, of the specification of spatial models. You know, there is, and in part, I guess, I'm at fault through GeoDa and the other software where you just click and you run the test and then run the model and you're done, right? Whereas the argument is that in some cases these models are really too simplistic and cannot provide causal interpretation. The reflection problem is useful. If you have the time, you should read the article, but it's useful to think about because it's really about when there is social interaction, how does it get to your individual behavior, right? Is it direct interaction among agents, which Mansky called endogenous effects? So you vote for a certain president, therefore you communicate that to me, therefore I vote for that president as well. That's endogeneity, right? Or is it observable exogenous group characteristics? We're all of the same religion, and all people of that religion vote for the same candidate. These would be called contextual effects. So they affect individuals as a group, but they're observed and observable, right? And then you have the magic ones, which do the same thing, but we don't observe them, right? So, for example, if people wouldn't tell you what their religion is, you know there might be some religion effect, but you can't measure it. You don't see it, right? And this is the hard one. This is called the correlated effects. So then in a model of social and spatial interaction, we have different kinds of variables. We have obviously the individual action variables or decision variables. We have group characteristics that are observable. We have individual characteristics that are observable, and we have unobservable individual characteristics. And then the basic model by Mansky has a variable y explained by the endogenous effect, which is formalized as the group mean effect. Now, notice the difference with a spatially lag-dependent variable. The group mean effect includes everybody. The spatial lag does not include yourself, as I just pointed out. So, as it turns out, this is a way in which the spatial lag model becomes identified. Whereas if you had, and if you have, I'm running ahead, if you have just a straight group mean as the endogenous effect, it is not separately identifiable. It mixes up with the other things. Okay, so then we have other group effects that we can observe, as I just mentioned, the contextual effect. So the Z are the individual characteristics, but they're affected by group membership, and then the unobserved ones. And to make things a little more complicated, we make the unobserved characteristics correlate among individuals in the same group. So this is the religion, you know, say, if it's observable, then it is a contextual effect. If it's not observable, then it becomes a correlated effect. So it's not always straightforward what these are. So then the model is, as any regression model, a conditional expectation, and a conditional expectation with the endogenous effect, the conditional expectation of y given the group, so that is how individuals influence each other. We have the contextual effects, which is the Z as conditioned by the group membership. And then we have the correlated effects, which are related to the group characteristics, but they're not observed. There's a random term, right? And so in the usual way, we need to get the y out of the right-hand side. You know, this is a structural model. We need to make a reduced form, and if we get the reduced form, then we see that all these parameters have 1 over beta in them, and they're all nice products and summations. So if you know anything about identification, it is that you stay away from sums and products. So if you have A times B as a parameter, then you can switch them around, B times A, and it's exactly the same thing. So in other words, you cannot tell A from B, which means, in technical language, they are not separately identifiable. Same thing if you have A plus B, you can make that B plus A, and again, you can switch their position, and you cannot separately identify them. You can identify the product, and you can identify the sum, but not the parts of the product or the parts to the sum, right? And so then Mansky spells out conditions that you need in terms of instruments or in terms of constraints on the parameters in order to identify these. The bottom line for the spatial models is that because of the particular structure of spatial weights with the zeros on the diagonal, that fixes the identification problem of the endogenous effects. So the endogenous effects in a spatial lag model are actually different, structurally different from the endogenous effects in the reflection model, which is more of an average of all the members of the group. In the spatial lag model, in the extreme, it's all the members of the group except you. But since we've seen these weights matrices are typically sparse, so it's not very many members of the group, so there's actually quite a bit of variability, and the variability is what gives you the identification. If there's no variability, you can't identify.
How do you think about that, that correction basically with given these spatial weights alongside the modifiable area from where it's basically like, is the assumption that the zero diagonal is correct, it stops being maybe as correct as you scale up the size of your
Well, as you scale up, everything changes, right? So the one thing that you do see, for example, is that scaling up changes the structure of the weights matrix. And so one thing is very easy to show is that the parameters do not remain the same. So if you have, say, an autoregressive structure at the micro scale, that doesn't necessarily translate to an autoregressive structure at the higher level scale, and vice versa. You know, so that is an additional constraint. And this is, I have to say, what makes a lot of more theory-oriented people uncomfortable, because to some extent there's a large degree of ad hocery in these spatial weights. You know, you just set them up for convenience. The bottom line is that you're trying to model an interaction phenomenon, and actually Mansky's the same, right? Where's the interaction? There is no interaction. It's a group mean. It becomes the group average captures or is supposed to capture all the interaction. And again, that's a simplification because you don't have actual interaction data. If you have interaction data, and that's where the flow stuff comes in, and it's really very interesting, but it's much more difficult to handle. So I can only talk about so many things. So how do we specify the spatial lag model? We have what we call, or what I call, a mixed regressive spatial autoregressive structure. So we have the usual regressive part, the x beta, and then the autoregressive part is the spatially lag dependent variable. Right? This is all very straightforward. Since, as we saw, we don't like to have dependent variables on the right-hand side, we move them over. As such, this specification is called the spatial filter. So what we have here is something very similar to detrending in a time series. But there's two differences. One is that simple detrending assumes that rho is 1. And a value of 1 for rho is not admissible. Because in order for this to work, this matrix, remember the variance-covariance matrix has to be positive definite and all that stuff. And when we talked about the different conditional models, some of these conditional models were not admissible because the inverse didn't exist. So if you have I minus W, when W is rho standardized, that matrix is singular. Okay, so there's no solution. You cannot solve the system. So that the parameter space does not include 1. So that's the first big difference with detrending in the time domain. The second difference is that the estimation of the parameter, the rho parameter, is not a straightforward exercise and cannot be done by ordinary least squares. But as such, this spatial filter is totally legit, right? It basically tells you what is the effect of x after I filter out the effect of the neighboring value. So in other words, this is a way in which you correct for the clustering in the data, which translates into less variability. So because of the lack in variability, you won't have as much precision. And so everything kind of hangs together. So there's quite a literature on spatial filtering, particularly in geography. It's even more ad hoc than the stuff that I talk about. So there's basically no data generating process for a spatial filter, say, based on eigenvalues. You know, you might see eigenvalue filtering in the literature, which is argued as a way to fix for spatial correlation. It really isn't. It can be in an ad hoc form that it just happens to correct for spatial autocorrelation, but it's not generalizable. It's not generalizable because for every different weights matrix, you have different eigenvalues and different eigenvectors. So it doesn't generalize in that sense. There's also no data generating process for eigenvectors per se. since they depend on the weights matrix. So you would have to have a data generating process for the weights matrix, which is typically not done since it's exogenous. So it's typical 2D trending. It's a way to deal with the scale problem, as I mentioned before, but we still need to estimate rho. So we have the spatial lag specification. An alternative form is the spatial filter form. Another important way to look at the spatial lag model is to think of the impact, the effect of a change in a variable on the change in the outcome. So as we, when we did the review of linear regression model, we said in a linear regression model, that impact is constant, it's fixed, it's beta. You change x, it doesn't matter what x is, the effect is always beta. Now in a spatial lag model, the effect is actually more than beta. And it's more than beta because of the feedbacks in the system. So in essence, if you solve the, to get the reduced form, you get this inverse matrix, I minus rho w inverse, that pre-multiplies the change in the x variables. So because of the rho standardization of the weights matrix, because the parameter rho is less than 1, you can use an expansion, a power expansion, to approximate the inverse term. And if you look carefully at this power expansion, you see that it's the effect, the immediate effect, the effect of my neighbors multiplied by rho, the effect of the neighbors of my neighbors multiplied by rho squared, and so on. So we keep moving further away, and each further ring gets scaled back down a little more because rho is less than 1, so it gets powered to a higher and higher power, so it's less and less effect. So this reflects this notion that everything depends on everything else. This also reflects a notion of distance decay. As you move further and further away, the effect of a change is smaller. This also brings us back to this interpretation of the simultaneous model rather than a conditional model. And you will find yourself interpreting your models as conditional, even though they are not. So you will write down, and I am willing to put money on this, that you will say, my house prices depend on my neighbor's house prices. Well, in fact, they don't, because you're modeling the whole pattern of all the house prices, and all the house prices depend on your house's characteristics, the x's, and then your neighbor's house characteristics, the x's, which of course do that indirectly because they affect the price of your neighbor, and then if you solve it out, there can't be any prices on the right-hand side, right? So it really shows the effect of the characteristics of the x variables at different locations in space, right? So there are direct effects and indirect effects. And there's a bit of a literature on this, on how to interpret the parameters. You know, how do you interpret beta? Should you multiply beta with its indirect effects? It's actually very simple algebra, right? The effect, the immediate effect is beta, that doesn't change. And then the spatial effect is all the rhos and the weights. That's what is added on to it, right? And so if rho is large and the weights have interesting structures, this effect can actually go quite far. But if rho is very small and the weights are very limited, then it doesn't go very far at all. So what this means is really you have to focus on this power expansion in the bottom here to get a sense of how important that is. And sometimes it's not important at all, and sometimes it really makes a difference. So how do you use this? This is actually, you know, quite cool. You can actually change the x variables in different parts and then see what that does, not just to that location, but to other locations. For example, in some work I did in India, we were looking at the effect of access to drinking water, regular access to drinking water, on the implicit price or rent of a house. And one of you has a very similar survey where it's self-reported rents, and then you try to relate that in a hedonic model to access to water. And so is it always connected? Is it a truck that comes more than once a week? Do you just have none at all? You have to go walk somewhere? All these kinds of things. So then, in a policy context, once you establish that there is in fact a connection between access to water and the price of a house, you can see, well, what happens if I, say, have the truck come every day in given neighborhoods rather than once a week? Of course, that affects that neighborhood, but it also affects the surrounding neighborhoods through the spillover effects. And so then you can quantify the effects of such policies, and oftentimes in policy analysis you do some kind of cost-benefit analysis. You want to quantify how the investment, say, in increased water access get capitalized in the value of the property that is affected by it. And so that's one way of doing this. How bad is it when we ignore a spatial lag? So this is an omitted variable problem. Basically, it's very bad, right? So, and you don't have to do math or anything to get this. If there is actually interaction going on and you ignore that interaction, you will be making a mistake, right? And since the spatial lag model is a model for substantive spatial interaction, if you drop it from the model, you're going to have all kinds of problems. And I have this little example that some of you might have already seen because I've been using it for years. So basically, we have a simulation where we simulate a setup where the spatial lag matters, right? And then we estimate a model without the spatial lag. So let's say we set rho to 0.1, we simulate the y's using the reduced form, then we take these y's and we regress them on x, ignoring wy, right? What does that do to the parameter of x? What does that do to the beta? So I'm cranking up the rho, it becomes more and more spatially dependent, and this is the distribution of the estimate for beta. The true value is 1, so you see when rho is 0, this is nicely centered around 1. As we crank up the rho, two things happen. One, the curve starts to move away from 1. That's called bias. So on average, this is the average of all the estimates, on average it's no longer on target. Second thing you see is the curve drops. What does that mean? The spread increases. Spread increases means greater variance, lower precision, right? So there's two things that happen: lower precision and bias. And so basically, you know, in some sense, all bets are off. All bets are off because the other parameters, the betas, are in essence picking up what is really due to the spatial interaction effect. So you might argue, well, I don't care. I mean, I just want to have the combined effect, right? But you should care, because if you ignore the interaction effect, not only are you off, so you're measuring something different, but your variance increases as well. So your precision is not what the OLS model would tell you it is. Okay. Spatial error model, much simpler. This is what I call nuisance spatial dependence. The pattern is in the error term. Error term is what shouldn't be there, right? The error term is not interesting. The error term should be random noise. If the error term is not random noise, there's two things you can do about it. One thing is to make sure that it becomes random noise. And you can do that sometimes by changing the model functional form, bringing in other variables. That's the ideal way, right? So you focus your attention and your effort on the signal. The noise is noise, random noise. You know, if you can't do that, and you know, in the past, especially in the small data world, very often you could not do that, then as much as you can, you try to model the structure in the error term until what you're left with is something that doesn't have any structure. So say we find an error term, well, error term you don't observe. So let me just talk about the error term. The error term has a spatial autoregressive structure. You put that structure in there, and the remainder error term of that process, the one we saw last week, is random noise. There's no more structure in there, right? So that's the way to think about it. If there is a systematic, bias, a systematic mean in the error term, you put that in the model and the mean is gone, right? So that's the way you have to think about it. So you're pushing the specification as far as you can until what is left is pure noise. So if you can do that by modeling the model, that's better, because that's about the signal. But if you can't, then you do that by modeling the noise itself and putting some structure in there to filter out, if you wish, the structure so that what's left is fine, is just pure noise. So there's no real substantive interpretation, and it's all about efficiency of the estimates. And as I mentioned before, in a big data world, efficiency becomes a secondary concern, because if you have 1 million observations, your standard errors are going to be so small, who cares? So the bottom line is that we have just a special case of what is called in econometrics a non-spherical error variance covariance matrix. That means that the off-diagonal elements are non-zero. We saw that in our discussion of covariance, spatial covariance last week. It's exactly the same thing. So how do we model this covariance? As we saw last week, we can have process models. For example, a spatial autoregressive error model. And we saw last week the variance covariance that results from that is this monster with this inverse term, right? And we also saw that if the weights are not constant across observations, that this gives us heteroscedasticity. So then from a specification testing point of view, this is going to be very difficult to tell one from the other, because they both pure heteroscedasticity and heteroscedasticity as a result of a SAR process are heteroscedasticity. So how do you know one from the other? It's another form of this inverse problem that we have. The good thing about the covariance matrix is that most estimation methods use generalized least squares or feasible generalized least squares or something along those lines. And for that, you need the inverse of the variance. So if your variance has an inverse in it, then the inverse of the variance does not. And this gives us a very easy way to do what we call later spatially weighted least squares, which is basically regressing filtered variables on each other. Right? Now, the other one that we saw last week, first the reduced form. So unlike the spatial lag model, the reduced form only pertains to the error term. So on average, because E, the error term, is on average 0, on average that disappears. There is no multiplier effect here, none. The only effect is on the precision of the estimates, and we'll see in a few weeks how we use this, or how we can use this structure in the error term to improve the prediction of our the prediction performance in an MSE, mean squared error sense. Right? So Kriging, for example, is spatial prediction, uses the structure of the error variance covariance matrix to improve the variance of the prediction. So we talked about the heteroscedasticity. Moving average model, here it's the other way around. The variance covariance matrix is fairly simple, but its inverse will have an inverse term. And so that is why you see very few applications of a spatial moving average model for large data sets, because you need to invert this n by n matrix, and that's not something you want to do for hundreds of thousands of observations. There's some other structures, as we saw last week. covariance, it's just a special case of modeling covariance. Instead of covariance for a general generic random variable, it's covariance for the error term. So we can have a direct representation, function of distance, and we can have conditional models, and then there's a couple of other things in the literature, but they're not used very much. What's the upshot? Same type of exercise. So we will simulate, here it is. So first thing you see, this curve remains centered on the true value. So there's no bias, right? But what you do see is that the curve drops. So the precision goes down. So especially if you use the OLS expression for precision, they're going to be wrong. So there is, in fact, one way around this. So OLS remains unbiased, but it's not efficient. As long as you can estimate this change in efficiency, you can stick with OLS. And that is the HAC approach, HAC, heteroscedastic and autocorrelation consistent. That we'll see later. So in the HAC approach, you don't do a spatial estimator for the parameters. You stick with your standard estimator, be it OLS or two-stage least squares, but you adjust the standard errors. Because as we saw, the standard errors are not right. So if you ignore that, then your t-tests will be wrong, your measures of fit will be wrong, etc. But your estimate itself remains unbiased, and that's a good thing because, I mean, at least in a small number world, unbiasedness is often better than consistency, because consistency is a large sample property and may not be reflected well in small data sets. As we move into a big data world, again, that becomes something else. So there's two other specifications I want to spend a little bit of time on because they are sometimes for the wrong reasons used a lot lately. And one of them is the so-called Spatial Durbin model, and I want to make a distinction here between what I call the classic Spatial Durbin model and then what, for lack of a better term, I will call an unconstrained Spatial Durbin model. So the classic model is really nothing but another way of writing a spatial error model. So if we look at this carefully, we have the standard regression specification, y equals x beta plus the error term. And the error term follows an autoregressive process. So the error term is lambda wu plus an error term. So we use the inverse to plug that new error term into the original specification. So we solve for u, we get u is I minus lambda w inverse times this e error term, the e one. So this is what I meant by pushing the model further and further. So u is spatially correlated, e is not. So after you put in the model for u, this e error term is not spatially correlated. So we take this expression for u and we plug it back into the model, right? So then we have y is x beta plus an error term, and the error term is this autoregressive one, which we have solved out by means of the inverse of the matrix. And then we multiply both sides by I minus lambda w. So what that does is y and x beta are pre-multiplied by what we just call the spatial filter, right? And the error term gets rid of its inverse, and what we're left with is the e. And e is not spatially correlated. So now we have a model with an error term that is not spatially correlated. But this is a model that has a couple of new terms, right? It has y, it has wy, it has x, and it has wx. So if you write this out, then you have a classic spatial Durbin, which is an analogy to the time series context where you have the very, very similar thing. And so On the right-hand side, we have a spatially lag-dependent variable, wy. We have the exogenous x variables, x. And then we have a new term, the spatially lagged x variables, wx. And we have a special set of constraints. So I have used the initial notation, and that's why we have lambda as a coefficient of the spatial lag of wy. We have beta as a coefficient of the exogenous variables x. And then we have the coefficients of wx. And the coefficients of wx are not just anything. They are the product of lambda with each of the betas. Okay. So that's a nonlinear model because it's the product of two parameters. I mean, if you want to make it explicit, it is nonlinear. The constant term, because wx, the spatial lag applied to a constant, think about it for a second. So if you apply the spatial lag to a vector of ones, what's the result? It's the average of the neighbors, right? All the neighbors are 1. The average of ones is 1. So the wx for the constant term and the constant term in the x are the same. That means that the constant term as such cannot be separately identified. This is one of these cases where you have a sum, right? They're in both the same explanatory vector is both in x and in wx. So you have to take it out. And so then you really can estimate the product, but not the terms separately. Right? And then in addition, for each of the other parameters, you have a constraint, a nonlinear constraint, that the autoregressive parameter times the beta has to equal the negative of the coefficient of wx that corresponds to that. So that's called a common factor constraint. And that comes straight out of time series. If you, I don't know if they still cover this, but in the old days that was a big deal because it was a way to estimate these parameters easily. You just rewrote the model with a lag-dependent term, and you were in business. In space, it's not quite that simple, but nevertheless, the common factor hypothesis still is alive and well. So we have, if we have k explanatory variables, then we have k minus 1 of these constraints. So obviously, in an empirical exercise, this is not going to be exact because you don't have lambda and beta. As I mentioned the other day, in classical statistics, these are constants, but they're unknown. So we have estimates. The estimates have randomness around them. So we can actually test, given our estimates, is it reasonable to maintain that these hypotheses hold, right? And if they do hold, if you do not reject this null hypothesis, then the proper model is an error model, not a lag model. And in an error model, remember, there are no multiplier effects. I'll come back to that in a few minutes. Right? So if this is really an error model, then there is no spatial multiplier because all of this is another way of writing this. So we write y equal x beta plus the error term with another regressive error term, or we write it as a spatial lag model. Right? This is the classic spatial Durbin model with the common factor hypothesis. Right? So then, somehow along the way, somebody forgot about this common factor hypothesis and looked at the model in unconstrained form. And you can do that. There's absolutely no reason not to, right? Because, and I never quite got this, but for some reason, there is a literature that thinks that it is more intuitive or more powerful to have a model with a spatially lagged dependent variable as well as spatially lagged explanatory variables. So this is what is called in the literature today the Spatial Durbin model. And of course, you still have the common factor hypothesis. And this is where it gets messy. Because if the common factor hypothesis is rejected, you go to an error model. That everybody agrees on. It's when you don't reject the common factor hypothesis. And that is where it gets tricky, because the alternative model is not nested. So it's not correct to say that if gamma 3 is 0, that you therefore necessarily have a lag model. It's actually much more complicated than that, because the lag model and the error model are not nested. You cannot get the error model out of the lag model and the lag model out of the error model. They're different animals, right? They're very similar in structure, but they're not nested in the way. A nested model is a model where you can get one out of the other one by imposing 0 constraints. So you could say, okay, let's put in a 0 constraint here. The only one that makes sense is lambda. So if we set lambda to 0 in here, what do we get? Do we get a spatial error model? No. What do we get? Lambda is 0 in 2 places. So all that's left is x. So if lambda is 0, we have a standard regression model. Right? So it's not that easy to impose constraints on this model because it doesn't nest. There are different combinations that are possible. And so there's nothing wrong intrinsically with if you reject the common factor hypothesis. If you reject the common factor hypothesis, there's one thing that you do know. It is not a spatial autoregressive error process. It could still be a moving average process or something else, but it's not an autoregressive process. So that's very clean, right? But if it's rejected, all that means that these nonlinear constraints don't hold. So then you have a model with a spatially lagged dependent variable as well as spatially lagged explanatory variables. And that's where it gets complicated. Because now let's do the reduced form. And remember, we used the reduced form to figure out what are the direct effects and the indirect effects of a change in x at each possible location in the system. Right? And so here we see that this is by no means that simple. And so the effect of our neighbor is no longer lambda times beta, which it was before, but it has two parts. One part is the same as the lambda times beta that we had before. The other part is an additional element. So this is something you have to keep in mind when interpreting these models, is that, and the way I like to put it is that the spatial lag model already has Wx in it. So if you add Wx in addition to Wy, you have it twice. And you better have a really good reason as to why it has to be in there twice, because it makes the interpretation of the direct and indirect effects very complicated. There's nothing wrong, right? To me, the argument has to be made that this is in fact more effective in measuring the direct and indirect effects. And one could argue that rather than adding Wx, you could fiddle with the weights matrix and get the same thing. But so anyway, if you see spatial Durbin model, your little tentacle should go up and you should say, careful. First of all, check the common factor hypothesis, and this is why spatial Durbin model is not built into GeoDa space. Okay, I'll do certain things, but there's also certain things I will not do, because I really don't want you to do this. I mean, or if you're going to do this, I want you to really think about it. And so therefore, I make it difficult. You can do it. You can construct a spatially lagged variable, plop that in there as an x variable. You can do all that stuff, right? But you really should think about it. So, as I said, it does not imply a spatial lag model, as is sometimes mistakenly argued. So the bottom line is these are not nested hypotheses, so you really have to think about it. Okay, then finally, the SLX model. This was introduced way back when as a spatial cross-regressive model. Basically, there's nothing to it. You know, and it's kind of interesting that this was kind of rediscovered through the Spatial Durbin route. Because, you know, in some literature, people would argue, well, you know, this WY is really too complicated. Let's just drop it. And so we have an X, we have a WX. What is the main difference here? The main difference is that WX includes local effects only. So where we saw the spatial multiplier is my own location, my neighbors, neighbors, and so on. So WX is in there, but then we go on. The second order neighbor, the third order neighbor. Here, it stops at WX. Right? So in other words, it sets these further indirect effects to 0. It chops it off. Is this reasonable? I'm sure that there's lots of empirical situations where this is reasonable. You know, in fact, you know, you could think of this as, you know, if you do marketing studies, right? You want to have the sales of department stores, and you model them by the income in the census tract as well as in the surrounding census tract, right? If you specify exactly the surrounding census tracts, that's WX, right? If you say, well, I don't know exactly how far it's going to go, you use WY. Because then your WX comes in through the back door, so to speak, in the reduced form, right? So, of course, in the literature, it's not just WX, it's then how can we change W, make it more quote-unquote general, right? And I always have to snicker a little bit because, you know, and this shows my age, I did all this stuff in my dissertation. And that's, you know, 1980. So there's nothing new to this. This has been visited and revisited. So sure, you can make the weights matrix more general. Sure, you can put parameters in the weights matrix. But at the end of the day, it's always the same thing. You're putting in some structure, whether the structure is exogenous weights pre-multiplied by something, or weights that are a function of distance and you estimate the parameter of that function. It's the same principle. You cannot solve the problem. You cannot model interaction with just cross-sectional data. So you have to do something. And then, from my perspective, this is really a matter of taste, whether you do this through the weights or through some function or non-parametrically. If you have a lot of data, by all means, you can let the data fit the function. And there's a literature on that as well, which is actually, to my taste, that's the best way to go. If you have the data, you let the data give you the functional form. So, as I mentioned, it's a model for local spillovers. You can, if you want to, have endogeneity in the WX. There's all no-brainer. It's all standard econometric techniques. If you have endogeneity, it's two-stage least squares. If you don't, it's OLS. So you don't need spatial econometrics. And that's probably why it's so popular. You know, you don't have to worry about it. But then there's this newer literature where you have, you know, more than one spatial lag term, and so then we're back into our reduced form. You have parameters in the W8 matrix, and then you have to worry about identification issues, And as I mentioned, we can do non-parametrics or semi-parametrics, which is really cool, actually. But just to give you an example of how you have to be careful what you're doing and before you get too excited about what you're doing. So in this SLX paper, there is an example of a spatial weights matrix that is a parameterized function of distance. So it's an inverse function of distance with a parameter, this gamma parameter, right? And the regression term is W, which is a function of this parameter, X, and then a beta, call it theta, right? Okay. So right off the bat, when you see this, your identification warning should go off, right? Anytime you see something that is a product of two things with parameters in both, you should be very wary. Is the data rich enough to actually let you identify both of these separately? Or can you only identify the mix, the combination of the two? And in fact, just for fun, if you keep this weights matrix with its parameter, but you take its log, then what you end up with is, you know, negative gamma times the log of dij. And the log of dij is just like a fixed weights. It's no longer parameterized, it's now fixed. So now you end up with something that looks like that. Minus gamma times W star, which is the log of the distances, times X times theta. And there is no way you're going to identify gamma and theta together, right? So this is why, even though it may look, if you wish, more sophisticated, more theory-based, at the end of the day, it doesn't help, because you still have a formidable identification problem. And for the life of me, I don't know how they end up with their estimates, but they do. It's iterative nonlinear least squares, so, you know, depending on where you stop and why you stop, I mean, you can keep going, but I would be very wary of this. I mean, the bottom line is your data rich enough to allow for these complex structures to be estimated from the data, right? Sometimes it can, sometimes it can't. Whenever you have sums and products, you have to be very careful. It's going to be really difficult. Whenever you have nonlinear models, it's going to be really difficult unless you have lots and lots of data. That's why, you know, the non-parametrics and the semi-parametrics is really a big data technique. You know, if you have 40 observations, forget it. You can't, you don't get the large numbers that drive these patterns, okay? So this is my review. This gives you a sense of the kinds of specifications that you can think about for your data. And then on Wednesday, we'll look at heterogeneity. And if I have a little bit of extra time on Wednesday, I'll show you GeoDa space again. But, you know, you have the book, you have the, you know, the detailed descriptions of, you know, click, 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 and this is what you get. So you should be able to get started with that.